All right, this is the continuation of the 1B1 to 1B2 notes. We had two last slides left on our Kahoot, and then I'll be switching over to do the 1B3 all in this video. So we'll get the 1B material out of the way. So we had these last two examples. They were just Kahoot quiz questions. So I'm just going to play against myself essentially. We have that Sue's paycheck is $1,040 for 40 hours of work. If she works 30 hours next week, what will her paycheck be? Okay, so we've got the same type of problems that we were dealing with before, where we can set up kind of labels for this. So if we think about the labeling, we could say that we have our um, week one and week two, and we have the money on top and maybe the hours on bottom. Okay. So in week one, she made $1,040 and worked 40 hours. Week two, we don't know how much she made, so that'll be our X, but we know that she worked 30 hours. So when we cross multiply, so let me get my calculator, we would write down the first diagonal is 1,040 times the 30. So that's 31,200. Just going to type that in, 31,200 equals. And then we're going to be doing 40 times x. So that'd be 40x. And then we need to divide to solve that. So dividing by the 40, because that's next to the x. You always divide by the number next to the x when you're solving these last steps. That'd be $780. So she's going to make $780. So I'm going to type that in. It's just said numerical answer only, so we didn't have to do the $, but I don't think I had it count it wrong if you did do it. Yeah. So $780. Okay. Now we're going to do our last question for the 1B2. So to set this one up, let's see what we've got. Ben needs to convert 500 US dollars to Japanese yen. $1 American is worth 123.3 yen. Of course, that was at the time they did that. How many yen will he have? Okay, and again, remember with these, you have to think about your labeling. So we're going to have our exchange rate, and we're going to have what Ben has, and then we're also going to have our dollars, and we're going to be comparing that to the yen. And it doesn't matter if you do your labels slightly different than me, as long as you label everything and put the numbers where they belong. So we've got our fraction is going to be, oops, let's change the color. Let's make it red. Let's see. So the exchange rate is the $1 American is 123.3 yen, and Ben has 500 US dollars. So we're trying to figure out how many yen he's going to have. Okay, so let's go ahead and do our calculator. So we've got 1 times x is just going to be x, and then we have 500 times 123.3. So we have x equals 61,650 because it was 1x. And was that 650? Yeah, 650. So 61, 650. And of course, we'll have to type that in. Now, same thing with Newton. You should be able to type in commas unless they say not to. You should, not type in the units because they don't want that on the Newton, but I did put it as an option in case someone typed it in here. Okay. All right. So that finishes 1B2. So now we need to open up the Kahoot for 1B3. And yes, since I played by myself, I am the winner of that Kahoot since there's nobody else right here. So let me pause my share real quick, and then I will open up the one for 1B3. Give it just a second. Sometimes it doesn't want to quit. There we go. All right, so let's find a new Kahoot. We're doing 1B3, and let me go ahead and share my screen again. Okay. So, like I said, this one, it's going to keep using proportions. We're just going to do a few applications of proportions for this. So let's look at our notes part first. It says proportion applications using CPI. So we need to define what this word CPI is. So we all know about inflation. That's the rise in the general level of prices of goods and services in an economy over time. CPI stands for Consumer Price Index. It's a monthly number that reflects changes in the prices paid by urban consumers for a representative basket of goods and services that are used to track inflation. So imagine, I think it was about 1982, 1983, it was $100 for that basket. So you had all these certain items like maybe milk, bread, an oil change, whatever it is that they consider to be the goods and services that they track over time. And that has been consistent since they started this. Those values, how much did it cost you? That's what the CPI value is. And it tells you, and we have them broken down a lot of times per year. So these are like the yearly CPI values. And you will be provided with charts in all of your questions on Newton. So you don't have to like look up these numbers online or try to memorize anything. So our goal is going to be to set up our template using appropriate labels, just like we did with our proportions in 1B.2, fill in the values, and cross multiply. You never actually put the year, like 2017 should not be in like a multiplication part of your proportion. The years are your labels. So they're like part of like what each fraction is labeled, okay? So just to make sure that you're not using the actual year number, like 2007 should not be used as a value in the cross multiplication. It's just a label. You're going to be using the CPI value and then things that they tell you that things cost. Okay, so let's look at this first one. My first car out of college cost $9,800 in 1987. This was not me. This was another one of our professors that wrote this question. And it says that what would that be in 2017 if it kept up with inflation? Now, just realize these cross multiplications that we're doing here, they are if we kept up with inflation. So if cars cost more in 2017 than what we come up with and when we solve this, that means cars are overinflated. If the cars at that time were less than what we came up with, then they're underinflated. They're not keeping up with inflation. Most things are overinflated nowadays, as we know that if you've shopped at the grocery stores. So we have 1987. Like I said, these are just going to be labels. And we have 2017. And we're going to put the money amount that they told us for the vehicle. So the vehicle money amount. And then we're going to put that with CPI, okay, for that specific year. So you can go ahead and grab the two CPIs up here. CPI for 1987 was 113.6. You can drop the two zeros if you want, since they're just zeros. 2017 was 245.12. So remember, this is the same bag of goods and services. In 1987, those only cost you a little over $100. Now they're costing like, closer to now that we live in, we're talking about $200 and almost $50. Okay. Now the car that we were given the price for was back in 1987. So that's 9,800. And we're looking for, if we kept up with inflation, what would be that price of that car? Okay, so that's what we're trying to solve for. And again, prediction based on the inflation only. So 9,800 needs to be multiplied by the 245.12. So that's going to be, let's write that down, 2402176 equals 113.6 times x. You always divide by the one that's next to x. So we're going to take that big number we just got and divide it by 113.6. And we're going to round to the nearest dollar. So that's 2114, and that 9 would bump that up to a 6. So 21,000. And then it was, sorry, when I changed to pen, it always closes that. 146. So that car that cost 9,800 back in 1987, that same exact type of car, if we kept up with inflation, should only have cost $21,146 in 2017. So it depends on if you could track what car that was and what the price is, you could see if the car prices were overinflated above the rest of the goods and services out there that they're tracking. Okay. So let's clear that. All right, let's look at another one. This one's already, or that was actually that one. It's worked out and I actually put it in great detail for you. But let's look at my second one down here. So it says if hamburger cost 38 cents in 1979, what would be the equivalent price for the year 2017? Now, I accidentally had a boo-boo on my chart up above. I didn't have the 2017 one there. So let's change this to match with one of the numbers I do have up there because I want it to match with what you would have been provided. I think I just had a typo and it was supposed to be the 2010. So let's look at this. So we have 1979, we have 2010, we have our hamburger, and we have our CPI. Okay. So the hamburger costs 38 cents. So if we write that in decimal form, like dollars and cents, that would be 0.38. We want to know what was its price in 2010. The CPI for 1979 was $72.60 for those goods and services. In 2010, it was $218.10. Remember, that's the same goods and services. This is how much they've increased in price. So we're going to take our calculator, multiply the 0.38 times the 218.10. And it was important that you wrote that 38 cents as cents in the 0.38 because it's the CPI is in dollars. So this is 82.878. And that would be equal to 72.60 times X. We need to divide by the 72.60. And that'd be $1.14 if we round to the nearest cent. So $1.14. Now I'm pretty sure hamburgers cost more than that probably in 2010 unless it was a special value menu. So looks like food probably has been overinflated too, but you'd have to double check that and you'd have to know what hamburger where did they buy the hamburger that cost 38 cents. Okay, now we have a try. So rounding to the nearest cent. So we've got if the price of an oil change is $45 in the year 2010, what was the equivalent price in 1985? Okay, so let's work out. We have our labels of 1985. It doesn't matter which one you write first. And our other label was 2010. We're doing an oil change. So OC over CPI. Just put my labels down. And then we're going to plug in our values for each of those for our proportion. So I have that the CPI in 1985 was 107.6. CPI in 2010 was 218.10 or just 0.1. 1985, we don't know. 2010, the oil change was $45. So we should be expecting something cheaper for the prediction here since we're going back in time. So this time our 107.6 times 45 is the diagonal where we know both numbers. So that's 4,842. We divide that by the one that's across from X. And if we round that to the nearest cent, we should have $22.20. So 22.20, and you do not need to put the dollar sign on these. If you did, it's okay though. I just know Newton does not have you usually put in a lot of the units. So just read your directions carefully. Okay. So we've got that one. We're going to try another one. So we have the price of McDonald's Big Mac was 65 cents in 1973. What would it have been in 2019 if inflation were the only factor impacting the price? That just means we're just saying what's the prediction. And then we simplified this table so that we have a lot less to look at. So we have our price of our Big Mac in 73. And then we've got our price we don't know in 2019. We know that CPI in 73 was 44.4 and CPI in 2019 was 255.657. So we're going to solve that by cross multiplying and solving for X. So multiply the two numbers you know that are in a diagonal together. So that's the 0.65 times 255.657. The one that's across from X is the one you divide by. So divided by 4.4. And that'll be $3.74 if we round to the nearest hundredth. Okay. All right. So now we've got a couple more questions just kind of dealing with CPI stuff. So let's look at this. If the average price of a home grew with inflation, the average price of the house in 1992 should have been 97,337. However, the actual price for a house in 1992 was 144,500. Did the average price of a house grow faster or slower within inflation? Well, if we're paying more than they predicted, because it should have been this, then our average house price grew faster than inflation. So that means we could throw out C and D. So just by process of elimination of how we read that, those two are out. And let's read the explanation of why. So it says the average price of a house grew faster than inflation because the actual is higher than the expected. That makes sense. The average price of a house grew faster than inflation because the actual is lower. No, that wouldn't make sense because if you're growing faster than inflation, your price should be higher. So it is answer A. So this one's just kind of a reasoning question. All right, let's look at this next page. It says the minimum wage in 1985 was $3.35, and it was $5.15 in 2005. If the minimum wage had grown with inflation, what would have been the expected value in 2005? Round to the nearest cent. Okay, so again, we've got 85 and 2005. I'll just do them in the order that they're here. So the CPI for 85 is 107.6. The CPI was 195.3 for 2005. Sorry, that glitched on the three. Okay, so let's talk about this for a minute. They've given you both dollar amounts for both of these. These are the actual wages. We wanted to make a prediction what would have been the value in 2005. So they're asking us, yes, we know this is what it actually is, but we wanted to know if CPI would have been the only factor, how would this $3.35 grown based on inflation, not based on what we actually know the actual wage to be. So we're trying to solve for the what if scenario. Since they gave us both, we already know the actual for both, but we want to know what could have happened in 2005 based on goods and services that have changed. Okay. So sometimes they'll give you extra information and you don't need all of it. So $3.35 times 195.3, that's 654.255. Divide that by 107.6. That would have been $6.08. So this is where things get a little scary for us because we're already seeing that, yes, goods and services are increasing, but we're not keeping up with it in our wages. Our wages are not keeping us at a place where we can even afford the cost of living. And that is truly what has been happening in our world. That's why people are struggling. So, they're not, this is what they were actually making. This is what they should have been making based on all the services and goods that people were buying, how they cost. Now, look at this one. It says the city of Tourist has 298 hotels with a population of 386,202. How many people do they have per hotel? Okay, so that's per one hotel. So if you think about it, this is people per hotel. So I'm going to put people on top. So 386,202 over 298. So per hotel, that's the divide word, per. And then we want to know how many do they have. So we're doing that per one hotel. So essentially, you could just divide this because if they want just a per one item, you're kind of just dividing the fraction that you already had, but we can still solve it by cross multiplying. So this would be 386,202 times 1, which is still going to be that, and then divided by the 298 since that's the one across from x. Round to the nearest whole. So that's a 9, so that's going to bump that up to a 6. So 1,296. That would be people per hotel. Okay. All right, here we have a question. San Francisco has 220 parks with a population of 883,000. San Diego has 340 parks. If San Francisco were proportional to San Diego in parks to population, how many people would San Diego have? So we're looking for the population of San Diego. So if we think about, again, it's up to you if you want to do population on top or parks on top, but you need to be consistent on both sides. So I would do maybe 220 over 883,000. That would be my San Francisco fraction. My San Diego fraction, then I'm going to keep parks on top. That'd be 340 over X because that's our population we're looking for. So this time the second diagonal, the 340 times the 883,000, that's the one where we know both numbers. So we'll multiply that. and then divide by the 220 since that's what's across from x. And this would be, I'm just going to type it in here. Oops, it went away. 1364. And then 636 rounded to the whole number. Yeah, the 4 will not round that up. So it'd be 1,364,636 people. That's an estimate of what we would say San Diego's population would be if the ratio of parks to people matched San Francisco. Remember, these are predictions. They don't necessarily mean they're exact. We're just saying if they're proportionate, here's what we would see. All right. Converting values to the words millions, billions, trillions, and to standard form and like to using scientific notation. So we kind of talked about scientific notation in class today. So if you have a word problem where the words match, so everything's in millions or everything's in billions, you really can just drop the word millions or billions and actually just solve the problem using the numbers, just the numbers that are in front of the word million or billion. But if so, and that's only if they match. So that means every single word in the problem that uses a like a word to describe the people would have to be the same word. So they would all have to be million, or they would all have to be billion. If they have a problem where they mix them, where some populations are million, but others are billion, you cannot just drop off the word. You need to use the powers of 10. So this is just to practice converting these and just making sure we're good with this. So 320 million, because I already have a couple examples written out, would be 320 followed by two groups of 3 zeros. So remember, that's 320 million. If I wanted to write that, if I can make that smaller, doesn't look like I can. If I wanted to write that using powers of 10, you could just write the two numbers you see there that are not zeros, 32, times 10, and then you would just count how many zeros you have. So 1, 2, 3, 4, 5, 6, 7. But that's not technically proper scientific notation. So proper scientific notation would be 3.2. We'd move it one place to the left, which means we add 1 to our power of 10. Remember, Lars. Okay. Now, 0.67 trillion. Okay, this one I'm probably going to write off using my pen to the side. So remember, trillion, if you think about your place values, like where is that in the place values? We had ones place values, thousands, millions, billions, and then trillions. So we have millions, billions, and then trillions. But this is not even a full trillion. This is the decimal point is saying we don't even have one full trillion. So this 6 actually is in the 100 billions place. So that right there is a tricky one because of the fact that you don't even have a full trillion. So it's going to be 670 billion. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if we write that just with counting the zeros, that'd be 67 times 10 to the 10th, because there's one extra zero in that group. And then if we fix that, we'd move it one place to the left, and it would be 6.7 times 10 to the 11th. Now, another way you could have gotten there quicker just to the scientific notation is to put this as 0.67 times 10 to the 12, because we learned we could replace the word trillion with 10 to the 12. And then you would have fixed it by move it 1 to the right, which means subtract 1 from the power. So you also would have ended up with that 6.7 times 10 to the 11th. And then 52.86 trillion. Okay, so this time we do have at least some trillions. So 52 trillion, 860 billion. Then we got our millions, our thousands, and our ones, or hundreds, whichever way you want to call that group. And then we've got to make that writing it as a number. So 5286 times 10 to the, oh, I guess we could have written these a little different. Let me go back on these. For this group right here, they just wanted us to write it using the word. So 320 times 10 to the 6. We'd still have to fix that, and it would become this. This one would have been 0.67 times 10 to the 12th. And then this one, they want us to just write it like this with the trillion. So 52.86 times 10 to the 12th per trillion. Again, we need to move that one place to the left. So that's 5.286 times 10 to the 13th. Okay. So what I fixed here in this middle column, sorry about that, is I was just writing all the numbers that weren't zeros and then just counting the number of zeros and putting an exponent there. They just wanted you to turn the word million or billion or trillion into its power of 10. I noticed that when I looked back at the originals from the Newton. So this would be 0.67 times 10 to the 12th, 52.86 times 10 to the 12th, 320 times 10 to the 6th. Okay. But the big issue is that when you fix it to proper scientific notation, doesn't matter how you got this part right here, whether you actually wrote the numbers and then all the zeros as a power of 10, or if you wrote it exactly as you see it here, you still have to adjust it to the same location for proper scientific notation. Okay. So we're just making sure we're good with that because our word problems sometimes will use, like I said, the words millions or billions or trillions. So let's look at this. So I have one worked out here for you. It says state A averages 205,000 deaths per year, while a population of 22 million, while state B averages 12,003 deaths per year with a population of 0.99 million. So these are all exact values. If state B were proportional to state A in deaths per year of the population, how many deaths would state B be expected to have? So not what they actually have, what would they have if they matched state A? So if you notice, I didn't label on this part, but this is state A and this is state B. The deaths totals are on top and then the populations are on bottom. So we're still solving for what would be the number of deaths in state B if it matched state A. Now notice I didn't change these times 10 to the 6th, and that's because they're both millions. So if you look at this cross multiplication, I don't make it scientific notation here because the million word is going to cancel out. Now, if I did, I'd still have something very similar, except I would have times 10 to the 6th for the scientific notation. And whether you fix that to be proper at this point or not is really not the point. It's the fact that they both have the 10 to the 6. So it cancels out. Okay. So you can just multiply and divide and get this. So it's 9,225 deaths predicted in state B based on its proportionality to state A. So actually, B has a higher death toll rate per population in its actual real numbers. We would be seeing a lot less deaths there than they actually had if it was proportional to state A. So the big thing here is that yes, you can turn these into times 10 to the sixes, or since they're both million, you can just leave it the word million. It still cancels out when you go to do the cross multiplication stage. So if this was million and the other one was billion, though, we'd want to change it to scientific notation. So we'll see an example of that at the end. I believe we have a try. Okay, there are 27 Starbucks in Atlanta with a population of 0.5 million. Brooklyn has 142 Starbucks with a population of 2.53 million. If Atlanta were proportional to Brooklyn in Starbucks to population, how many Starbucks would Atlanta have? Round to the nearest whole number. So we're looking for Atlanta's missing Starbucks. Even though we know their exact number, we're trying to make them proportionate to Brooklyn's population and Starbucks. So we have Atlanta and we have Brooklyn. We're trying to figure out Starbucks and population, and we're solving for what would Atlanta's Starbucks number be if it matched with state B, which is Brooklyn, or city B, Brooklyn. So they had 142 for 2.53 mil, and this one was 0.5 mil for the population. And again, I'm not going to need to change those to times 10 to the 6 because when we cross multiply, we'll get a million on top and a million on bottom, and that'll cancel out. So you can just work with the numbers if you have both of them in millions. So 142 times 0.5, and then divide that by the 2.53. Looks like they would have around 28. So just one more Starbucks than they actually have. So they are actually pretty close to what they are predicted to be. The actual value is 27 in Atlanta. And if they matched Brooklyn, they would have had one more. Okay. Proportionately. All right. And then our last slide is one of those where I said we would have different values. So one's millions and one's billions. So we need to make sure we use powers of 10 to make sure we get the correct values. So it says Chicago is home to 2.706 million people, and the city sees about 55 million visitors each year. China has a population of 1.393 billion. Notice their population does not match the measurement system that we have in our Chicago one. Okay. It's different population values in terms of the word. If the visitors were proportional to Chicago, how many visitors would China expect? Write your answer in scientific notation rounded to two decimal places. Anytime we're writing our final answer in scientific notation and they're asking you to round, don't round until you put it into proper scientific notation. Okay. So try not to round too early or you'll get the wrong answer. So let's set up our ratios here. So we have Chicago, we have China. It's very different comparing a city to a whole country. So we have, let's do population on top and visitors on bottom. Doesn't really matter as long as you put numbers where they belong. Chicago is 2.706. Now I am going to convert everything to scientific notation because we have millions, but we also have billions. So that's that one. Visitors is 55 million. And I'm not going to worry about that not being proper right now. I'm going to do all my calculations and I'll fix the proper scientific notation part at the end. And then China's population was 1.393 billion. So that's times 10 to the ninth. And then we're trying to find the visitors value. So if we write this out, we would do the cross multiplication of the two numbers that we have and that are both in the same diagonal together. And that's going to be equal to, or the 2.706 times 10 to the sixth times x. Now, I want to talk about this for a minute. So I'm going to rewrite this for just a second, and I'll tell you why. I always do this on purpose, and I know you're thinking, yeah, she did it on purpose, right? Because this is where you get lost because your time symbol now looks like your variable. So sometimes what I like to do when I write scientific notation in a problem with where I have a variable is use a different variable other than x. That will help part of it. Or use the fact that multiplication can always just be written with a parentheses. Okay. Because remember, scientific notation technically is still a multiplication of a number times a power of 10. So if you do it that way, that'll save you from getting confused with what your variable is. You just have a part for a number and a part for um, your power of 10. Now, if you were typing that into Newton, remember you do have to write it in their form of scientific notation with like the time symbol. So let's look at what we get when we work this out. So I'm going to work out, and actually you can type all of this in if you're very, very careful. You could go ahead and divide this over, and I'll show you that why that might be helpful. It's because you're going to get some stuff that cancels. So let me write this out. So this would be x equals, and on top we would have the 55 and the 10 to the sixth, just writing all my pieces. And I would also have the 1393 and the 10 to the ninth. And then I'm dividing all of that by the 2.706, I can type, and the 10 to the sixth. Okay. Now, because this is a division bar, and actually I'm going to write it a little bit different. I'm going to use my line here to show that this is a division bar. You do have a 10 to the 6 on top and bottom. So since this is all multiplying on top and bottom, you could cancel that out. That helps you just with some of the typing in. But when you type in multiple things that are being multiplied together on either a numerator or a denominator in your calculator, it's best to type it all in using a big parentheses around the whole thing. So for my top, I'm going to be doing 55. I opened a parentheses before I type that, times the 1.393 times the 10 to the ninth. So I'm not putting parentheses around each individual one. I'm using the time symbol on my calculator, but I put a parentheses around the whole numerator, okay? Then I'm dividing that by the bottom number, which after I canceled my 10 to the sixes, that's 2.706, okay? Now that gives me this number, not in scientific notation, it just gives me the answer. So we're going to have to adjust this once we Write it out. So it's 28,313,008,130. And I'm going to go ahead and write maybe 4 or 5 decimal places because remember we said don't round till the very end. Okay. They want us to write this in scientific notation, rounded to 2 decimal places. Well, this right now isn't a regular number. I want it to be scientific notation. I have to make sure I get all of this decimal point. I can only have one digit in front of it. So I have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So that'd be 2 point. Now I can round to the nearest hundredths, 2 decimal places. That'd be 8, 3. The 1 will not bump the 3 up. And then this is times 10. And then we moved it, remember, left. So we're shifting this left. That means we're going to be adding to our exponent. Well, we didn't have an exponent to begin with. So that means you're just going to put how many moves you had. So that was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there it is. So that would be the number of visitors. And that would be in, if you wanted to write it, if you wanted to say it in words, you'd have to look at this. This is hundreds, thousands, millions, billions. So it's 28,313,008,130. Okay, but they wanted it in scientific notation. All right, so that right there is the end of the 1B3 and all of the rest of the notes we were supposed to do today. So I'm going to work on the 2A video because remember that one you need to watch before you see me again on Wednesday. That is the class that we're missing, and there will be a special Kahoot just of questions for y'all to do with that.